Kia ora koutou, no mai, haere mai. Welcome to lesson 13 of Introductory Physics. This lesson is going to look at work and energy. So far we've only considered forces and the resulting motion. Now what we're going to do is look at the effort that it takes to cause those forces. As usual, we'll jump over and we'll just have a look through the slideshow. So lesson 13 on work and energy. Our goals for today are to be able to define and calculate work, distinguish work done on an object versus work done by an object, explain the concept of energy, and define a couple of different types of energy, that is potential energy and kinetic energy, along with calculating those. And finally, we'll look at the work energy theorem briefly. So firstly, work. What is work? When we're moving something by applying a force to it, it takes effort. Right? Applying a force and causing a motion takes effort. You might be pushing a box with a force equal and opposite to the friction on that box, or it might be gravity that's applying the force and the object falls towards Earth's center. It accelerates downwards, or if it reaches terminal velocity, it travels downwards with a constant velocity while the force is applied. In both of those cases, the application of a force has caused an object to move some distance. Now think about these two different scenarios. If you push a box on a very low friction surface, just give it a quick little push, and then it slides for 10 meters because the surface is so low friction that, according to Newton's first law, once you let go of the box, once you push it but you let go, you release that push. Once you release that push, there's no force in the horizontal direction because the friction is so low. Obviously, for there to be absolutely no force, then the friction would be zero. But as long as the friction is very low, it might still make it 10 meters. So consider a scenario like that, and then consider one where you've got a rough surface and you will still want to move the same identical box 10 meters, but now you have to push it the whole way. Which of those scenarios requires more effort on the part of the box mover? Does it take more effort just to give it a push and then it slides 10 meters, or does it take more effort to push it consistently for the whole 10 meters? Hopefully we're all in agreement that the second scenario will take a lot more effort. The first scenario only takes a little bit to increase that velocity. And because we haven't said how fast the box is going, we haven't said what the velocity is going to, we haven't really talked about how much acceleration we need, so we haven't actually talked about how much force we need to apply and for how long at all. We could just give it a very small amount of force for a very short time, give it a tiny velocity, and it takes a long time, but it does still travel those 10 meters, or we could give it a bit more force and it would do that, those 10 meters more quickly. We haven't talked about that, but regardless of what scenario exactly looks like, there is only a small amount of force at the start to get it moving and then nothing for the rest of those 10 meters. Whereas the second box, where you're pushing it on a rough surface for 10 meters, you are applying force the whole time. That whole 10 meters, there is force being applied to that box by the box pusher. And if you stopped applying a force at all for an instant, then the box would stop as well because friction would force it to decelerate and come to rest. So the second one, we hopefully will all agree, takes a lot more effort. That effort is defined as work in physics. When you have to apply a force to cause an object to cover some distance, that is work. Work is one of those words that in everyday language we use a lot. There's a lot of different definitions for work. In physics, it's very specific. It is the effort needed to, through the application of a force, to cause an object to travel some distance. And so therefore we calculate it according to that statement. We calculate it as the product of force and distance. Work equals FD. W is the symbol for work, so W equals FD. The units, since it's a product of force and distance, is going to be a product of the units for force and distance, which is newtons times meters. However, because work is such a common property that we're looking at in systems, and in fact it's a type of energy that we're going to see, we define it as joules, which we write as a capital J. I've just noticed that slide says the next lecture. I've actually put energy into this lecture, so we are going to talk about that in this lecture, not next lecture. But because we have a force times a distance, there are of course plenty of other possible units for work. It doesn't have to be joules, although joules is the SI standard. But you could use Newton meters, you could use kilogram meters squared per second, you could use pound times foot, you could use tons times centimeters squared times minutes to the power of -2. Those are all valid units for work or for energy, but the standard is joules, and so we tend to stick to joules because it is the one that's easily converted with other quantities, compared with other quantities, I should say. Suppose we want to lift a box of mass 10 kilograms up 1 meter. In order to move the box at a constant velocity, so we're not accelerating it upwards, we're just moving it at a constant velocity. In order to do that, we need to provide a lift force that is equal and opposite to the box's weight force. We know the weight force. The weight force is mg. So if we are applying a force of mg for some distance h, then the work we have done is mg times h, or just mgh. If it's 10 kilograms, we'll set gravity to 10 just for simplicity, and we're going up 1 meter. That gives us a work done of 100 Newton meters, or 100 joules. So our work to lift a 10 kilogram mass up 1 meter is 10 times 10 times 1, 100 joules. Technically, we would need to apply a slightly greater force at the very start in order to accelerate the box, because initially it's at rest, and then we're moving it at a constant velocity upwards. That means acceleration did technically occur. We can't change from v equals 0 to v equals some positive value without an acceleration, even if it's very brief. However, when we're dealing with situations like this, where we talk about moving something at a constant velocity, so we're just balancing the opposing force, like gravity, we tend to ignore that little bit of extra force at the start, because what we assume is that the velocity is pretty slow. So there wasn't really much acceleration that happened. If the velocity is slow and there wasn't much acceleration that happened, then you weren't really applying a greater force for very long at all. And in terms of our significant figures, that would end up being negligible. So instead of 100 Newton meters, it might end up being 100.2 Newton meters, but that we're not going to four significant figures, so we don't actually care about that tiny little bit of extra energy needed to accelerate it in the first place. That said, there are scenarios where we will talk about acceleration. We're going to come to that. But for scenarios where we're talking about balancing the forces and when we're talking about moving at constant velocities, we'll often just sort of ignore that change in velocity, where it goes from 0 velocity to some positive velocity, which we're going to assume is very small, and then we can ignore that force needed to change the velocity. Work is a product of force and distance. Forces are vectors, so you may expect work to be a vector. However, work is the effort needed to provide that force across that distance. So force has a direction, but the work actually doesn't. The way we define work is that it's a scalar. Work is a scalar. It can be confusing because work may be in different directions, and it may have different values going in different directions. It may take a certain amount of work to push a box one way and a different amount to push it a different way, and so on. Pushing a box sideways versus lifting it upwards is going to be different amounts of work. So you may think the work has a direction involved in it, but it doesn't, because the forces involved have that direction that can change the amount of work needed, but the work itself is still a scalar. It's just the amount of effort that we're defining as work. Let's suppose we want to lift a box that's twice as heavy up a specified height. So we're not changing the height, we're just still moving the box up height h. However, the mass is now 2m. We still just have the same formula. Mass times gravity is the force we have to apply, and we're doing it over some height h. So mgh for our initial box and 2mgh for our second box. So doubling the force, doubling the mass requires doubling the force for our lift, and therefore it doubles the work. Similarly, if we want to double the height, then you can see easily by that equation that we're just going to get 2h instead of h, and that'll give us again double the work. So double the distance, double the work. That's assuming the force is unchanged. Note that when calculating the work, we actually only use the component of the force parallel to the direction of motion. When we're lifting straight upwards, that's easy because we are talking about going straight up. We'll often limit ourselves to 1D motion, so it's pretty straightforward because the force is either going to be in line with or directly opposite to that direction of motion. But sometimes the forces are 2D even if the motion is 1D. And in that case, you need to think about the force component parallel to the direction. For example, in lesson 10, example 3, we talked about pulling luggage along a floor. We were using a strap that was at an angle of 18 degrees to the horizontal. So the force we were applying to the object was actually not horizontal, but the resulting motion was horizontal. In that case, to calculate the work done on the luggage by the person, you would need to only use the horizontal component of the force. So it's the horizontal component times that distance in that direction. Sorry, I shouldn't say horizontal component. In this example, it's the horizontal component because the motion is horizontal, but it's the component of force that is in the direction of the motion of the object. That is what the work needs. So what can actually do work? You might be tempted to think that only living things can do work because we are the ones that in our everyday lives, we apply work to things. We go and push something or pull something, or we might make an animal do it. So we are living things and we make other living things also do work. But in reality, a work is simply a force times a distance. It's force applied to an object consistently while that object covers some distance. Many inanimate objects are doing work all the time. For example, gravity. Gravity is always doing work on anything that is falling downwards. Technically, the Earth, the gravitational attraction to Earth is doing the work. So the Earth might be seen as doing that work. The Earth is doing work on everything that falls towards it. You might phrase it that way. It's a bit of an odd way to phrase it. But work is occurring due to that gravitational force, and there's nothing living, nothing animated involved, just objects falling towards Earth. Friction is a force. Friction obviously therefore can do work. Friction results in work because friction is a force. If an object is covering some distance while friction is being applied, that can result in work. However, you have to be careful about the direction of that force and the direction of the motion, because we've defined friction as being in the opposite direction to motion. So how does that work? Remember that the friction is doing work on is applied to the box. The friction from a surface is applied to the box. But that means that the box must be applying an equal and opposite force to the surface. And if the surface is applying a friction force to the box that's opposing the motion, then the box is applying a force to the surface in the same direction as the motion. I might actually just use the document camera just to hopefully make this really clear. You have a surface, you've got a box on the surface. If the box is our system, then we know that there is a friction force opposing the motion. So we've got velocity going that way. We've got a friction force opposing the motion that is from the floor onto the box. And that's how we normally work with it, because the box is our system in most cases. However, if you think instead about the floor as our system, then the box, remember Newton's third law, the box is applying an equal and opposite force to the floor, right? So the force from the box, friction force from the box onto the floor is in the same direction as the motion of the box. So we've actually got all these different directions and vectors to consider. So you've got to be very careful about your system and everything. We're going to talk more about that at the end of this lesson. And if you do push a box while it's experiencing friction, and you do so at a constant velocity, then the work you do on the box is a force times a distance, but the work that the box does on the floor is exactly the same, because you are balancing that friction force. So therefore that friction force must be equal and opposite to your push force, which means that the force on the floor from the box must be equal and opposite to that friction force, which is therefore exactly the same as the force that you're applying to the box. So while you apply a force to the box to balance friction, that friction is going to be exactly the same force vector. And since you're traveling in the same direction, you are going to have the work done by the box onto the floor being the same as the work done by you onto the box. So that was a nice big convoluted statement, but hopefully you can start to grasp the idea that there's just always work being done whenever we've got forces and motion. Generally, we say that work is done by the object causing the force and done on the object reacting to the force. But Newton's third law says there are equal and opposite forces in the interaction. So if you do work on a box, is the box doing work on you? Remember that the force is only in the direction of the motion. If you are pushing the box, the force you apply to the box is in the same direction as the motion. So that means you are doing work on the box. However, the force the box applies to you is opposing that motion. It's in the opposite direction. We count that as negative work. So the box would be doing negative work on you because it's applying a force to you while moving in the opposite direction. Negative work, though, is the same as saying work is being done on that object. So you could say that the box is doing negative work on you, but in reality, we always phrase it as saying that you are doing work on the box. They mean the same thing. It's just a matter of that direction and that force being the same, the force being in the same direction as that displacement, as opposed to opposite to it. In the previous example, so far, as I said, we've talked about opposing another force. We had gravity when we were lifting, or friction when we were pushing. So the work we were doing was just to oppose a different force, and we had no real change in velocity. As I said, you would have to have a little change to get it moving, but it would be fairly minor compared to the work done to actually keep it moving at that constant velocity. However, we often encounter scenarios where a force is causing an object to accelerate. Just about everything involving falling is going to involve acceleration, because the acceleration due to gravity is 9.8 meters per second until you reach terminal velocity. So just about every example of falling is going to involve acceleration. But of course, we can also accelerate things in other scenarios, like pushing a box from rest until it reaches a speed of 2.5 meters per second, which is a relatively high jogging speed, but certainly easily attainable. We can no longer assume the accelerating forces are negligible, because we have a significant amount of acceleration. If we push that box from rest until it's reaching a speed of 2.5 meters per second, then we have accelerated it significantly. We can't ignore those acceleration forces. So now we have to consider the work done to accelerate the object. The work is still exactly the same. The work is still just force times distance. It's just that the force is now greater than it was when you were pushing it at a constant velocity, because you're now opposing friction and then applying some more in order to cause that acceleration. Unfortunately, this distinction is not formal. There's no strict rules. As you've seen with a lot of physics so far, there is no method that you can just memorize and learn. You can't just use maths and figure out the solution. You have to actually think about the scenario, think about the directions involved, think about the forces, think about the motion, think about which component of the force is in the direction of the motion, or is it opposed to it, and therefore what's doing work on what. So you have to think all of this through. There's no shortcut. There's no just memorizing the maths and applying the formulas. You need to do the physics in order to understand what work is being done by what onto what. For example, let's just work through an example and hopefully figure out a bunch of this stuff. So we're going to stick with our simple scenario of accelerating a box. I often talk about boxes and just rocks and simple things because it is simpler physics. When we start dealing with more complex systems, when we start dealing with anything that can deform or bend or change shape or rotate or anything like that, then we start getting more complicated. So we'll keep it simple with a nice straightforward box on a surface. We have a 10 kg box. We want to accelerate it from rest to 10 meters per second. The friction coefficient is 0.2, and it takes 5 seconds to do this acceleration. Both the push and the motion are perfectly horizontal. So you are pushing a box that is perfectly horizontal, the motion is perfectly horizontal, and you accelerate it up to 10 meters per second in 5 seconds. Step 2 is to calculate the push force on the box. Right, I skipped step 1. Step 1 is the frame of reference. You should be well practiced at that by now, so I've skipped it. Right, but do take a moment to think about the frame of reference. Pause the video if you need to, but obviously I will be referencing it as we continue because it's necessary, that first step. I'm just assuming that you're well versed at it now and have done so without me needing to explicitly state it. So the box is at rest and it accelerates at a constant rate of up to 10 meters per second after 5 seconds. So therefore the acceleration, because we have constant acceleration, it's just change in velocity over change in time, that is plus 2 meters per second. The box has a mass of 10 kilograms, so the net force must be 10 times 2, which is 20 newtons. F equals MA, 10 times 2, 20 newtons. But there is also a friction force. Friction force is equal to mu times normal force. Because the motion is horizontal, the surface is horizontal, our friction force is going to just be mu times Fn, and Fn is just going to be equal and opposite to the weight force. So the friction force will be mu times mg, which gives us a friction force of negative 19.6 newtons. Right? Negative 19.6 newtons because we're opposing the motion. So the applied force must be the net force minus this friction force, but we're minusing a negative, so we actually add it. So we have a push force of 39.6 newtons. Hopefully you followed all of that. That is just stuff from previous lessons. There's nothing new in what I've written on this slide. If you need to, pause the video and have a go at following through all of that math and physics, but hopefully you can agree that the push force must be 39.6 newtons while this box is accelerating. The next step is to figure out the distance, because we know work is force times distance, so we need to figure out the force, which we just did, and the distance traveled. Distance traveled is pure kinematics. We've got an initial velocity, an acceleration, and a time. Therefore, we know that the distance traveled is 25 meters. Again, pause the video and double check that if you're not confident, but that is pure kinematics. We should be pretty practiced at that by now. As you can see, this is why we need to build up those tools to start with. It's why we start with simple kinematics, then look at forces, and now move on to energy, because it all builds on the previous topics. If you didn't grasp kinematics, go back and practice it now. There's no way to solve a lot of these energy problems if we don't have that grasp of kinematics. Finally, once we know that force and that distance, we can calculate the work. That is a force of 39.6 newtons for a distance of 25 meters. So the person pushing the box, or whatever is pushing the box, it might be an engine or a motor, whatever is pushing that box has provided or has done work on the box of work equals force times distance, which is 990 joules. But not all of this work went into accelerating the box, right? Some of that work was used to balance friction. When you pushed, or whatever was pushing, some of that was balancing friction, and some of it was going into accelerating the box. That means some of that work was going into opposing friction, and as we said already, the box does work on the ground as a result of that friction. Friction means the box is doing work on the ground. So you're doing work on the box, or the pusher is doing work on the box is doing work on the ground, but the box is also accelerating. So while the pusher has applied 990 joules of work on the box has done 490 joules of work on the floor. That's just that friction force times the distance. The distance is still the same. The box has still traveled 25 meters, but the friction force was only 19.6 joules, 19.6 newtons, which gives us 490 joules of work done by the box on the floor. So we had only 500 joules being used to actually accelerate the box. So 990 joules was done on the box, 490 was done by the box to the floor, and 500 was actually used to accelerate the box. So we've got all these different energy values. What's the actual answer? Is it 990, 490, or 500 joules? It depends entirely on how the question is worded. If the question was how much work was done on the box, that means how much work did the person or object pushing the box do on it, then it would be the full 990 joules. If the question was how much work was done to accelerate the box, then the answer would be 500 joules, because the other 490 was applied to the box but used by the box to apply work to the floor in the form of while overcoming that friction as a result of that friction. How much work was done by the box? That would be the friction. That would be that 490 joules. So the only way to answer this question correctly is to ensure you actually understand the scenario and understand the question. Read the question carefully. Maths cannot help you here. This is all physics and reading, right? So English, a bit of reading comprehension, read the question, understand the scenario, and then you'll be able to answer it. So let's go back and actually have a look at that question. What was the question? The question was, calculate the work done to accelerate a 10 kilogram box from rest to 10 meters per second. So the work done to accelerate a box. That means that our answer is actually that second option. The work done to accelerate was 500 joules. Note that you can actually simplify your calculation here. We didn't need to worry about the friction at all. All we needed to know was the net force, because the net force times that distance would give us the 500 joules. So we didn't actually have to calculate the friction at all. But by all means, there was nothing stopping us calculating all of that information. Next part is energy. So we've talked about work. Now let's talk about energy. Work has the quantity, the units of joules. As we saw, any quantity with the unit joules is an energy. It's a form of energy. Work is one type of energy. Specifically, it's talking about transferring the energy. It's taking energy and applying it to another object. But there are other types of energy. Energy in general is the capacity to do work. The capacity to do work. Doing work is the use of that energy, but things can have energy without doing work. So they might have energy ready to do some work, but they're not doing the work with the energy. So energy can just be stored in objects, but it can also be used to do the work. Consider a spring which you stretch out. The spring now has the ability to do work on whatever it is attached to. You've got a mass on the spring, you pull it out, you let it go, the spring will do work on that mass by applying a force to accelerate the mass back towards its original unstretched length. That ability to do work is the energy. So that spring has the ability to do work when you pull it out. When you let it go, it then does the work and it retracts to its original length. And as it does so, it does work on the object by pulling it, by accelerating it back towards the center. What we're going to look at is mechanical energy, which is based on the position or shape of something. We call that potential energy, and mechanical energy based on the movement of something, which we call kinetic energy. There are other types of energy, non-mechanical types of energy, which are chemical and so on. We're not really going to get into those, although we will meet them later on in the course. As a little bit of a sidetrack though, is torque and energy. We met torque in our lesson on circular motion. We said it's a force times a lever arm, force times a distance. Therefore, it's got units of Newton meters. And we said that Newton meters are joules. So is torque in joules, and is it a form of energy? Short answer, no. Technically, yes, you could write the units for torque as joules. We don't. We write it as Newton meters for this reason, because technically it's not an energy. Torque has a direction. Torque is a force times a direction times a distance, and that gives us a direction for the torque. Remember that a torque always resulted in either positive or negative rotation, clockwise or anti-clockwise. There was a direction involved. That means that torque is a vector. Energy, however, is always a scalar. Energy is a measure of the amount of effort needed, or that is the potential for effort. So torque is not an energy. If you're really interested, you can go and look up more on that. The long answer I'm not providing, but you can certainly go and find a long answer if you are intrigued. But short answer, torque is not an energy. For now, what we will look at in terms of energy is kinetic and potential energy. As I said, two different types of mechanical energy, but there are plenty more. So the first one, potential energy, we're going to talk about. Potential energy is so called because it has the potential for doing work. It is stored in or by the object due to its position or shape. For example, a compressed spring has potential energy because it wants to decompress. It wants to change its shape. A stretched rubber band, exactly the same. It has potential energy because it wants to contract back to its original length. So it's got a change in shape, which is storing that potential energy. And an object at the top of a building has potential energy because it will fall downwards if released. Gravity will cause it to accelerate downwards, so that's potential energy as well. As soon as you release it, it can do work going downwards. There are other types of potential energy, such as chemical potential energy and fuel. Fuel is combusted and that releases the energy and uses it to do work. Gravitational potential energy is probably the most common one that we'll deal with in this course, but we will meet the others as well. We have to do work on an object to lift it against gravity. We already talked about this. If you want to lift an object some height, the work you have to do is mgh, the mass times gravity times height. The energy is stored in the position of that object, and if you release it, that energy will manifest in downward motion. It will accelerate downwards. We already saw that the work done was mgh, as I said. That, therefore, is the gravitational potential energy. That work that you've done to lift the object is all stored in the object as potential energy, ready to turn back into motion when you release it, to accelerate that object. Potential energy, though, is always relative to some point or origin. We talked about the idea that you lift an object up some height h, you give it potential energy of mgh. That means that if you choose your h position to be 0 at some point, then at that location, that object has no potential energy. What we'll generally do is choose potential energy origin as being ground level, or the final position of the object, or the lowest position, etc. Right? There's no one strict rule, but usually one of those is going to be a suitable choice. Then you define the potential energy relative to that position. So technically, the only point at which an object has no gravitational potential energy with Earth is when it is right in the very center of the Earth, and we never actually get there. So we could go and figure out the potential energy of an object on an Earth's surface compared to the center of Earth, but that's going to be such a big number that our changes by lifting it up a meter will be very small compared to that original amount of potential energy. And it just gets really messy and hard to work with. So instead, we just choose our own origin, because we're allowed to do that. We choose an origin as some useful position within our scenario. For a spring, we will almost always set the origin to be its uncompressed length, the end of the spring when it is uncompressed. Then if you stretch it or compress it, you are changing that. So if you stretch the spring, you're moving some distance x away, or if you compress it, you're moving some distance x the other way. Then we use that position to calculate the potential energy. We'll talk more about springs in a moment. Actually, I think we'll talk about springs next lesson. Units for potential energy. Potential energy is just a type of energy, so it still has the same units as energy, which is joules. A quick question just to test your appreciation of the discussion we've had around potential energy. You've got a ball and you're lifting it up 2 meters and you're doing it 3 different ways. Firstly, you just lift it straight up from the ground to the top of some column or pillar, whatever it's standing on. In the second, you're lifting it up a series of steps to get it to that same height. And in the third one, you're rolling it up a slope to get it to that same height. In which scenario does the ball have the most gravitational potential energy, and in which does it have the least? Hopefully you've got an idea in mind already. The answer is that it has the same gravitational potential energy in all 3 scenarios, because the potential energy only depends on the final height of the ball. Right? It doesn't matter how it got there. It only depends on that final height, mgh. That's all that matters for potential energy. It might take different actual amounts of work to lift the ball by each method, whether you've got to overcome some friction along the way, or whether you're lifting it up a certain height above its final position and then letting it go and it drops back a little bit. The amount of work you would have to do would be greater, and so on. So the work that you have to do to get the ball to its final position certainly depends on how you get it there, but the potential energy that it ends up with only depends on its final height. The last part of this lecture, I think it's the last part, is kinetic energy. So kinetic energy is talking about motion. Kinetic, similar word origins to kinematics, right? Kinematics talking about motion. Kinetic energy is the energy of something just by virtue of being in motion. So when an object is in motion, we say that it has kinetic energy. This kinetic energy is equal to the work done on it to accelerate it from rest to its final speed. So that kinetic energy is the energy done just to accelerate. Remember, that's different from the work done on the object, because the work done on the object might be greater if it's overcoming friction, or less if there's some other force as well involved and you don't have to push it as much. So it might be different, the amount of work you have to do on the object, but the work done to accelerate the object is what determines the kinetic energy. And that is just equal to half mv squared, where m is the mass and v is the velocity of the object at that point in time. Therefore, the work needed, we've just said that the work needed to accelerate it is that kinetic energy. So the work needed to accelerate an object from rest to a speed v is also going to be a half mv squared. You are allowed to just look at this formula and memorize it. Many people have already seen this and they're already familiar with it. You are allowed to just memorize it if you want. However, I do have a proof here, which you don't need to memorize, but you can certainly follow it along, and it doesn't hurt to do so. It helps improve that overall understanding of what we're talking about with energy. So let's assume that we went at some constant acceleration a, from initial velocity of 0 up to some final velocity v. Then our acceleration is just going to be v over t, because we've gone from 0 up to v, so the change in velocity is just v, and we've done it in some time t. We don't know that time t yet, but we know that the acceleration will be v over t. So our force that was needed, remember this is the net force because we're talking about the acceleration of the object, so the net force needed was ma, which is mv over t. The distance that we have traveled while accelerating that object is going to be given by kinematics, vit plus a half at squared. Hopefully we'll remember that change in displacement, change in distance formula. I'm using distance and displacement a little bit interchangeably here. That's because we're assuming that for this calculation, we're assuming it's moving in a straight one-dimensional line in one constant direction, in which case distance and displacement will be exactly the same. Right, so in this case, distance and displacement are the same. So our displacement is going to be VIT plus a half AT squared. VI though was 0, so we just have a half AT squared, and we already said that A was V over T. So we have a half V over T times T squared. One of those T's will cancel. We have half VT. Therefore, our work, force times distance, force is mv over T, and distance is a half VT. We have a half mv squared. Right? The T's cancel out again. So the acceleration and the time taken end up being irrelevant in terms of figuring out the work done to accelerate an object up to some final speed v. The work is just dependent on the mass and that final velocity. You might do it more quickly or more slowly, but once the object reaches that speed v from a distance, from an initial velocity of 0, the distance and the time are irrelevant. The acceleration rate is irrelevant. All that matters in terms of the kinetic energy is the work done to accelerate the object, and that is just a half mv squared. As with potential energy and energy in general, kinetic energy is just energy, so it is joules. Another, I think I mentioned in one of the previous lessons, to do some unit analysis when you get these sorts of new equations, which I'm just presenting to you. By all means, do that here as well. We've got a half mv squared. Double check that a half mv squared gives us units of joules, which you'll remember was Newton meters, and you remember newtons was kilogram meters per second. So do double check all of that. I have written it out there, but it's a good habit to get into to double check. Oh, right, there was one more part. I thought the kinetic energy part was last, but this is the last one. The work energy theorem, and this is just stating what we've already been talking about, the relationship between work and kinetic energy. If you apply work to accelerate an object, then that work, remember that this is the net force in terms of the work, the net force, because it's the work done to accelerate the object, so not overcoming friction or any other forces needed to oppose other forces, just the energy to accelerate the object will be equal to the change in kinetic energy. Quick example using that theorem. Two identical cars are moving. Car A is traveling exactly half as fast as car B. How much more work was done accelerating car B compared to car A? So they're identical. Car A is traveling exactly half the speed of car B. How much more work was done? Kinetic energy of either car is given by a half mv squared. M is the same in both equations, but since the velocity is doubled, 2v all squared becomes 4v squared. So that means that a half mv squared, if you double v, becomes 4 times a half mv squared. So the kinetic energy is quadrupled with a doubling of kinetic energy. So that means the kinetic energy of car B will be 4 times as much as the kinetic energy of car A. And according to the work energy theorem, the work done to accelerate the object is just equal to its change in kinetic energy. And since we're assuming from rest, the change in kinetic energy is going from 0 up to its final, so therefore 4 times as much work was done on car B compared to car A. And that is the end of this lesson. So we've introduced work and energy. These are, as I said, these are terms that we do use in everyday life, but you need to be careful about making sure you're understanding the physics definition of these terms.